everyone. My name is Dervla O'Reilly, Senior Event Manager with MIPI Alliance. Thanks for joining us today for the MIPI A-PHY Auto Industry Forum. Today's event is presented by Raj Kumar Nagpal, co-chair of the MIPI A-PHY Working Group, and Ido Cohen, co-chair of the MIPI A-PHY Working Group. Today, the forum will be moderated by Ariel Lazri, Vice Chair of the MIPI A-PHY Working Group. So a few things to note before we start the session. Today's session will be recorded. We'll make it available by the end of the day tomorrow, and that will be available in the Knowledge Library at mipi.org and also on our YouTube. All telephone lines are muted, and we will encourage Q&A. And also we'll be running a poll session. So we encourage you to get engaged and take part in the poll. We have two segments today. The first segment is an overview of A-PHY, and we'll take a look at the new features and updates. We'll then open up a Q&A for that segment. And then we'll move into segment 2, which is an interactive session. And we'll take about 45 minutes for that ending session. We'll be running the polls and we'll do a Q&A in that segment. So I encourage you to type your questions in the Q&A panel and we'll go ahead and get started. So with that, I will hand over to Peter Lefkin, Managing Director of MIPI Alliance. Peter.
Thanks, Dervla. And I'd like to welcome everybody to the first MIPI forum of the new year. With a focus on MIPI A-PHY and automotive. We look forward to continuing these types of forums on a range of different topics for MIPI Alliance. I think this will be a unique opportunity to obtain an overview of MIPI A-PHY v1.1 that was just publicly announced last week on the 18th of January, and engage as much as we can in this type of environment in an interactive environment, looking forward in terms of looking forward with requirements and thoughts on the next generation of A-PHY. We continue to see increased interest and engagement both within MIPI on the specifications and the member ecosystem regarding A-PHY now that it has been available to MIPI members since June of 2020. As with all specifications, the development of the specification is one piece of a larger set of initiatives that occurs to support the implementation and adoption of a specification and products. I expect that you'll see a number of interesting developments within this year as development continues on member products and future enhancements and evolution of the specification, which you'll hear about today. In addition, we continue to support our mass MIPI Automotive SerDes solutions set of specifications in the areas of the physical layer, security, functional safety, and further adoption of MIPI protocol specifications in automotive, including camera and display. Chips, camera sensors, IP, among other products for MIPI members are anticipated in 2022. If you look down the member list of MIPI Alliance, you'll see a wide range of OEMs and Tier 1s and other players in the automotive industry who are paid members of the Alliance. It's very interesting to see the dynamics at play within the auto industry. One can look back at the evolution of the mobile industry from MIPI's inception in 2003 to see a bit of a parallel in the importance of standardization and the evolving nature of the ecosystem. It's certainly an exciting time for the automotive industry, and we're pleased to see a wide range of MIPI specifications adopted and reused for the automotive ecosystem. MIPI continues its focus on mobile specifications and fit-for-purpose use for many other applications areas, including automotive. This is not new, it's not aspirational, it's been happening for over 10 years. With that and this brief introduction, I'd like to now hand it over to Raj Kumar Nagpal of Synopsys, who's the co-chair of the MIPI A-PHY Working Group, and he'll provide an overview of MIPI A-PHY. Thank you very much. Raj, you're
Raj,
muted.
we can't hear you.
I hope I'm on unmute now. I think we can start, correct?
You are. Thanks, Raj.
Okay, thanks, Peter, for the nice introduction, and appreciate all the effort going on in organizing this. So let's start with MIPI A5, and I'm going to take you guys to the MIPI A5 overview, all the spec developed so far, and my colleague Ido will take you to the next planned, future for the A5. So let's start with what exists today. So basically, MIPI A5, is evolving and is really taking the place for the physical layer, which is going to really exist for long channels, which are like 15-meter in the automotive domain, wherein the noise is one of the major consideration. So basically, MIPI A5 is actually the first specification which is really going to standardize the physical layer in the automotive segment. And it is going to start with, if you really see today, there are proprietary solutions which are not any work group driven, but they are, individually driven by companies which basically connect bridge to bridge, and these bridges are connected to sensors through C5 or D5 today, okay, or I3C kind of solutions. So this is existing today. So the transition of this is going to happen in a manner wherein this bridge solutions will remain, but these proprietary interfaces will get replaced with the standard A5 solutions, which will be basically going to be a middle, position. And then later on, these bridges will also be removed, and then proprietary things will be away. Then directly A5 will interface with the sensors, which will be basically having a MIPI protocols. So this is going to be visible here, which is the future of A5. Okay, so this is the way we consider it is going to be a right business model. It is going to reduce the cost of the real implementation, and it is going to make a reduced BOM, and it is going to be more efficient way of really implementing the solutions. Okay, so this is one a basic slide. Here I'm sharing with you how the MIPI A5 is basically this is a physical layer which is going to have multiple interconnects, which can be coaxial line or shielded twisted pair or shielded parallel pair cables. Okay, and basically it is a point-to-point interface wherein you have got source which can be connected to camera or display sensors, and similarly sync, it can be either maybe display or it can be ECU kind of things. So it's basically a physical layer which is going to be a long distance with multiple interconnect possibilities, and it is going to support both downlink and uplink. It is by default, it is a asymmetric interface wherein uplink is actually lesser bandwidth compared to downlink. And this is actually the primary requirement for the uh, uh, ADAS or ADS solution. So this is the primary target of this physical layer. Okay, so it is directly going to couple to CSI to DSI, DP or EDP protocols. Okay, the performance is 16 gigabit per second per lane. Okay, and this is going to support 10 to 15 meter of distances. Again, distance is a function of quality of interconnect. So primarily one should look at the S parameter performance as a more electrical, compliance requirement. Okay, but generally it falls to 15 meter for coaxial line, and for shielded twisted pair we claim it to be 10 meters. It's a high noise immunity, ultra low packet error rate. Okay, it stands for -19 packet error rate. Supports bridge based and endpoint integration support for automotive coaxial and shielded twisted pair or shielded parallel pair channels. It supports power over coaxial line, power over cable also. Okay, so it is going to support multiple functions: power delivery, data delivery in a full duplex mode. Of course, it is asymmetric because of the need of the application requirements. So this is a very top level overview of MIPI A5, The next, so basically this is a little bit more detailed, a little bit of one layer down from my previous slide, wherein I'm trying to share here that how my source, APHY source and APHY sync are getting connected. This is your interconnect solution. We call this particular PCB as AND node PCB, okay? And then this cable can be shielded twisted pair, shielded parallel pair, or coaxial line, okay? Power delivery is supported as one option wherein you can transfer the power to the sensor using this approach. There is no dedicated power requirement at the sensor. This physical layer will support the power delivery also. So this is a very top level, solution. We go a little down. So this particular slide is giving an overview of the data rates supported in A-PHY 1.0, okay? And then it is going to give a little more on other aspects, but let's start with the data rate. So by the way, MIPI A5 is supporting multiple gears like gear 1, 2, 3, 4, 5. It is all downlink, and then there is an uplink, okay? In the downlink, we have got, gear which are supporting different data rates like 2 gigabits per second, 4 gigabits, 8 gigabits, or 12 and 16 gigabit per second. The modulation supported are here. Gear 1 and 2 are supporting NRZ. Gear 3, 4, and 5 are supporting PAM-X, like PAM4, 8, and 16. This is my modulation bandwidth, which is basically Nyquist bandwidth, and then this is the effective throughput of my data delivery. Okay, and this is all downlink. In the uplink, I'm supporting for A5 1.0, I'm supporting basically 100 Mbps, and effectively it is 50 Mbps throughput. Okay, and this is an NRZ modulation. So this is basically a very, very top level view of my gears in A5 and data rates. And other salient features of this physical layer are, it is supporting EMC noise sources, which are very prevalent in automotive environment. And then the beauty of MIPI A5 is that it's designed to be very robust in a very noisy EMC environment. I cannot give you exact numbers because of this public, but if you really want to see the exact EMC noise sources which this PHY is able to tolerate, you can look at our specification. Okay. There are two main primary profiles supported by this A-PHY 1.0. Profile 1 is basically our low cost power optimized solution, which is primarily supporting NRZ, which is gear 1 and gear 2, and then targeted packet error rate is 10⁻⁹. Okay, maybe it will be leading to around 10⁻⁻12 bit error rate. Okay, for profile 2, it is more optimized for very reliable high EMC noise solutions capable of very high reliability, and the packet error rate targeted for this profile is 10⁻⁹. So it's a very, very robust packet error rate. Okay, interoperability, this is fully interoperable. You can move from one profile to another. Okay, and higher profile, like higher gear implementation, will always ensure that the lower gears are supported. Okay, so this is very robust, very reliable, very complete interoperable solution supporting different profiles based on your application need, and it's a very broad, offering from the MIPI A5's domain. Okay. Now, there are some, deep dive. We are giving very top level overview of MIPI A5. So MIPI A5 Profile 2, basically, this is a very top level block diagram wherein you have got, protocol layer, adoption layer, link layer, retransmission, PCS layer, PMD, and then this is your channel. This is basically a very top level. The beauty of this physical layer is it is supporting retransmission, and then it is supporting NBIC. So retransmission, if there is a failure in the packet detected, then my sync can request a specific packet to be retransmitted, that is retransmission. And then if there is a failure, and then this failure is appearing because of any EMC noise attack, then my receiver has a mechanism to really cancel this noise, which is called narrowband interference cancellation, which is basically a mechanism at the receiver end wherein it can request the source to transmit a specific pattern, training pattern, and then receiver can really detect the signature of this interference aggressor and really cancel it out. And this is a scheme which is basically narrowband interference cancellation. Okay, and with these two, you are able to achieve a packet error rate of 10 to the power minus 19. This is only because of these concepts. And these two concepts are very much desirable from a automotive perspective because of a very large noise bursts you get. So you have to have a mechanism to handle the noise cancellation. Okay. And by the way, this particular mechanism is not going to be visible to the upper layer. This is local event of RTS and NBIC. So this is basically here, link layer is not going to really get affected. There is a defined time wherein this, retransmission event is allowed. So within 6 microseconds is the total delay from my source to sync for the packet delivery. Okay, so that's the way. Otherwise, this particular physical layer is very efficient in terms of overheads. It's 90% net data ready. So only 10% is the max overhead, which might be consumed in managing the RTS or NBIC, or really handling the, traffic, handling the aggressor rejection. So you have got a very efficient implementation, and this is very, I must say, this is a very top level architecture. So this particular slide is giving an overview of aggressor event happening, and then how my receiver is going to really correct the situation. Here you see, without retraining, without canceller, you actually lost you got a very high EMC noise, and you lost your link is lost. Immediately on the detection of packet failure, then the retransmission event is really initiated. Okay, now it depends upon the packet lost. If you need only retransmission, and if you need retransmission plus just-in-time cancellation, which will basically be a specific training pattern which will be coming to the receiver, and receiver DSP block will be using this to LMS algorithm to detect the spectral response of the noise, and will really be ensuring the adaptive filters to really position or adapt to reject this EMC noise aggressor, and then you revert back from PAM2 to PAM4. So your constellation is also recovery based on the based on the performance. Your constellation will go back to the original constellation. So this is a very intelligent mechanism used in VPA5 on handling the aggressor noise cancellation. Okay. So then actually now this slide is basically giving an overview of A-PHY 1.1, which is the next version of the specification. Initially it was A-PHY 1.0, and this basically slide is giving enhancements made in A-PHY 1.1. And remember, A-PHY 1.1 is backward compatible to A-PHY 1.0. So your ecosystem is fully respected. So major updates in A-PHY 1.1 is basically we have doubled the uplink data rate from 100 Mbps, now it is 200 Mbps. We have provided optional support of PAM4 in Gear 1 and Gear 2. The advantage is that you will use lesser baud rate, and then your interconnect bandwidth requirements will be less. So your for Gear 1 and Gear 2, your uh, interconnect can be cost optimized without really putting the performance loss, and that you achieve by having a baud rate, and PAM4 modulation is going to reduce your baud rate. Okay. And then very big thing which is actually appearing in A-PHY 1.1 is supporting STQ cable, which is a shielded twisted quad cable, which is basically two differential pairs, and this is very common in the automotive industry. And this is basically going to give you few advantages. On the top, it is going to double your downlink traffic throughput from 16 to 32 bit, and then other options of Q port, which I will get you through in the coming slides. So you can look at it. Basically, we have added PAM4 support in Gear 1 and Gear 2, and then we have doubled the uplink from 100 to 200 Mbps. Okay, so this is basically basic enhancements. And by the way, A-PHY 1.1 is taking advantage of STQ cable, and lot of digital blocks are really not really changed because you have effectively not changed your per lane data rates. So that is the advantage that this particular STQ cable is provided. Okay, so same high noise immunity EMC RF noise source aggressor capabilities are unchanged. Okay, they are same between A-PHY 1.1 and 1.0, and data rate enhancements are there. It is going to double your data rate due to STQ cable. Okay, so this is all the enhancements in A-PHY 1.1. So here is basically a cable which is supported in A-PHY 1.1. You can see it's a dual differential pair. Because of dual differential pair, you have different configurations, which is dual downlink configuration, wherein both the pairs are being used in the downlink, and per pair you are having supporting 16 gigabits per second. So double downlink you get. So ultimately you get 32 gigabit per second downlink. Uplink is same 100 Mbps and 200 Mbps, which I shared in my previous slide. Now, in the asymmetric configuration, which is basically another configuration in A-PHY 1.1, wherein downlink is 16 gigabits per second, but uplink is 4 gigabit per second. This is some of the applications wherein you need higher, data rates. So we are supporting this. In the third is symmetric configuration, wherein uplink and downlink are similar, and which is 16 gigabit per second supported. Okay, I need to move little fast, guys, because of the time constraint. So basically, MIPI A-PHY is actually a part of the solution which we call MIPI Automotive SerDes solution, which is in short we call MAS. And this is basically a complete solution for ADAS and ADAS application in the automotive segment, wherein you have got sensor to display, and this whole ecosystem is part of MIPI solution and offerings, and this makes a complete solution coming from MIPI in the automotive segment. So I'm little moving fast because of the time constraint. So these are the solutions specifications which are clubbed together under the mass, um, which is MIPI Automotive SATA solution, wherein you have camera, display, and then you have got support for VISA also, and then you support other protocol layers based on your requirement. And this is basically a physical layer, link layer, protocol, multiple protocol adoption layers, and supporting multiple protocols. So this whole is basically a mass solution offering from MIPI. MIPI mass guiding principles are here. Very top level, we need a PHY which is very robust. Okay, so this is high noise immunity PHY, which is supporting multiple EMC standards. This is our first guiding principle for the physical layer. All the protocols which are actually an advantage with MIPI are going to be used. No new cost to be really incurred in really adapting it. And then we are supporting functional safety and security, framework in the mass guiding principle. And this is actually going to be a total robust solution from MIPI for ADAS and EDS, requirements. So with regard to MIPI A5 system modeling, this is basically, I'm going a little fast. It is basically profile 1 system modeling, which we really did in EDS. As sort of this complete solution is available to MIPI members. They can download and use it. And this is basically profile 2, which is actually a solution in MATLAB environment, which is also available to MIPI member companies. This is a complete spec implementation. You can look at it. If you have any query, you can ask me questions, but we need to just push a bit. So this is sort of a PAM16, scatter plot, wherein you can see all the D-labs here, and you can really see how the noise cancellation is really achieved for the aggressor. So your DSP block is adaptive filters, and they're going to counter these noise components. Okay, and this is the summary. So we have established ecosystem with multiple vendors working on A-PHY compliant chipset. Okay, it's a clear and forward-looking roadmap and planning. A-PHY 1.0 is released in 2020. A-PHY 1.1 released in this last month, December 2021. A-PHY next is our in progress discussions, which my colleague Guido will take you through, and then multiple pulse which we are supporting, and we are adding few more pulse like HPI and Ethernet to allow this solution becomes rich in really accepting multiple traffic types. Okay, and then supporting multiple advanced use cases with clear advantage on industry standard error-free links, very high bit error rate, packet error rate as per -19, seamless integration. A-PHY 1.1 and A-PHY 1.0 are fully forward and backward compatible solution. Interoperability is well achieved. So this is the very reliable offering from the MIPI in the automotive segment, and I hope I have given you all the basic insight so far.
Thank you, Raj. Appreciate that. So now let's move into the Q&A segment, introducing Ariel Lazri, who will be the moderator. Ariel. Actually, you're on mute, Ariel, if you don't mind unmuting.
Thank you, Devla, and thank you, Raj, for the presentation.
Yeah,
we received a
welcome.
couple of questions on the chat window here. The first question we received is about how does packet error rate of 10 to the minus 19 translated to bit error rate under harsh environment.
Okay. So basically, see, profile to A-PHY is supporting PAMX. Okay. So basically, it is a baud rate. So it is a symbol. So if I talk of PAM 16, so you get 4 bits per symbol. Okay. So your baud rate is 4 gigabaud. Okay. So really speaking, packet error rate is basically related to symbol error rate. So basically, if you really see in our one packet is consisting of 1000 symbols. Okay. So 1000 symbols means it stands for 3 symbols makes one packet error rate. So packet error rate of 10 is power minus 19 is basically a symbol error rate of 10 to the power minus 22 kind of thing. Okay. And then if you talk of bit error rate, it will be further multiplication. So it is basically 4 bits make one symbol and 1000 symbols make one packet. You have to calculate it accordingly.
Okay, so we have a factor of 1000 about there plus.
Yes, correct.
Yeah. Okay, I got the second question here, which is about power over cable. This could be challenging when we have a high current requirement for the sensors. Challenging for high current requirement for the sensor. And then the second question in this question is whether the bit error rate will go up and lose data for long distance under this noise conditions.
Okay, so there are two questions. One is that current is going to be less for some sensor application. So the power which we have targeted today is 6 watt. And basically, we can increase this power delivery based on the requirement. So the new spec for the POC, power over coaxial, is under development, and we are going to really ask the audience what kind of power levels will be more, suitable for, maybe very power consuming sensors. Please advise in the poll questions, and we are going to work on that. Okay. Second question is, the POC is going to affect my packet error rate. Actually, we have got a very well defined POC noise profile, and the POC noise profile is actually well defined, wherein we have designed our receiver to really counter this noise profile and still not get affected for its packet error rate performance. If you really want to see more details, you look at our system modeling diagram, and then you can really appreciate that how we are canceling the POC noise at the receiver. So actually we kill this noise in a way, and our packet error rate is not going to be impacted by it.
Okay, thank you, Raj. So the next question we have is, do we have a cable edging impedance calibration time? And to which vehicle lifespan time? So
can you repeat? I lost
yeah,
the question.
the question is written that way. Do we have cable edging impedance calibration time?
Okay.
Time with the vehicle lifespan time. I think
okay. So yeah, I understand. Okay. So basically, cable aging is a very, very important subject for the automotive industry. And basically, if you really see our EMC noise sources, they are actually done with the physical aging of the cable. And then in basically, in MIPI, instead of seeing the impedance, degradation, we capture it by the shield degradation. Okay, shielding degradation. So in a way, we are really capturing the degradation of the shield with the time over the lifespan of, I think it is 20 years, 15 to 20 years. We take the shielding impairment and we take the EMC noise impact because of shielding impairment, and we take that EMC noise source in our receiver as a noise source available, and then we really design our receiver adaptive filters to adapt to this degradation. So
Yeah.
this is what best I can reply to you at this stage. Yes, there is a degradation and there are robust mechanisms to handle this degradation without impacting your packet error rate. And if you really want to understand more details, please read our system architecture application note on this subject.
Right. Thank you, Raj. So we take the shielding degradation and the cable aging into account into our system model, and there's no, and we can accommodate that. That's good. I have another question here on about the future generation of MIPI A5 specification. Will a portion of the channel loss be allocated for the PCB trace?
It is even today allocated. By the way, if you really look at A5 specification, there are three segments of interconnect. One is end node PCB, which we called EN. There's a PCB which is basically on one side of the box. There is a PCB loss. There's a PCB return loss requirements, which is there in the specification, which need to be met. And there is a channel. Channel is basically your coaxial or ST shielded twisted pair or shielded parallel pair. And then there is a end node PCB on the other side of the connecting box. And that again has to respect the return and insertion loss specification. So it is a complete system is going to be these three elements. Of course, your point of interface is after the end node PCB. Your spec compliance need to happen at the connector interface, which is basically after the PCB. So your electrical design need to take into account the PCB degradation, PCB loss also in a way.
Thank you, Raj, for this answer. I have another question about the tooling. So what tools are available for debugging and testing of the APHY link? And will standard debug tools such as oscilloscope be able to be used? And then there's a third question there. Given the just-in-time counselor, how do standard debug tools handle this?
Okay.
So maybe I will repeat first the first question: what tools are available for debugging and testing of the APHY link? That's the first one.
I would say this is a very big engineering, I can speak on it for hours, but how much time I have? So basically, it is like this. There are three levels of tool. One is tools at the design stage. There are tools at the design for test, and there are tools for test. Okay. So if you want to see digital block performance, you have to use BIST kind of things. Okay. If you really ensure analog, then you will have your analog design test benches to validate the performance. Okay. Now we talk to the test tools. Okay. Test tools are also on the two kind of things. One is data traffic, interoperability, link partner based tools. Then other kind of tools are physical layer characterization tools, which will be like a generator, oscilloscopes, wherein you are doing all kind of eye diagram, jitter. So there are tools available, and this is this PHY is no way very different than any other general PHY. I mean to say whatever tools you use in like any PHY, the same standard tools will be used here. They are available in the market. Of course, there may be changes in terms of fixture design, or there will be dedicated fixture solutions. Those kind of things are going to be dedicated. Otherwise, standard tools are anyway are going to be used. Everybody is going to work with them. Nothing special needed. For the link partners, data traffic, you will have a protocol analyzers, which will be again dedicated to the A-PHY specification. And this is designed with the specification in mind. They will be available from vendors who are giving standard solutions in the protocol domain. That's our understanding.
Okay, thank you, Raj. And this will be also applicable to the just-in-time counselor. I think that was one of the questions.
Okay, so if you really want to see the performance of just-in-time canceller, so if I really see the steps involved in GITC canceller is first, whenever my receiver is going to receive a bad CRC of the packet, and when it sees multiple bad packets, then it understands there's a strong EMC noise source presence, which is not allowing my receiver to really extract the signal. It will advise the source through the uplink to send it a training pattern, which is called GITC pattern. GITC pattern will be initiated by the source. It will come to my sink, and my sink adaptive filters need to really use this pattern, and it is a known pattern for the receiver, the sink. Then it has to adapt its DSP filters to really detect the noise signature and cancel them. So this is the whole process of noise cancellation, NBIC. Now there are various steps, like there will be state machine test wherein my detection of failure, CRC failure, then request on the uplink to my source, then source is sending the packets, GITC packet, receiver receiving the GITC packet. I mean, so for every stage, you need to have your BIST mechanism if you really want to do it. And then once the packet is received, your adaptive filters are going to work as desired. I mean, so this is something I have not thought of. How will I really do my receiver GITC operation, but I can see I will give a known noise, and then I will see that my adapted filter tap coefficients are expected. So I will have a mechanism to take out my FFE, DFE and see that it is rejecting the noise. So there are different stages wherein you need to really keep your, you need to plan to really, it is a plan at the design stage. How are you going to test this block? This is all I can speak at this stage.
Okay, thank you very much, Raj. I'm not sure how much time we still have. Devla?
2 more minutes, Ariel.
We can take one more question. Okay. Okay, maybe this question, the next question, in a quad deserializer, how does packet retransmission affect synchronization between the sensors?
Okay, so basically, can you repeat your question, maybe, Ariel, again?
So in a quad deserializer, how does
Quad deserializer, okay.
yes. I just lost the
How?
question. In a quad deserializer, how does packet retransmission affect the synchronization between the sensors?
Okay, so by the way, so your question is, I am receiving, there's a quad, so there are two differential pairs, and I am receiving a packet, and I found on one of the differential pair, the packet is lost. Another differential pair, it is okay. And then I don't know from which source this packet is generated. I think that is your question. So by the way, in MIPI A5, there is a mechanism to detect your channel. Okay. So channels will be numbered like 0 and 1, and you know which there is a mechanism to transfer the, like, source to sink, there is a way to swap your traffic. Okay, so there is a mechanism wherein you can swap your differential pair. Sync to source swapping is possible, and then you will detect source 0 is going through differential pair 0 is going to your receiver 0. Okay, and if say it is not 0, then you will really change, you will swap at, there's a soft swap mechanism at the receiver. So you will first do that, and basically at the training time, at the initialization time, this will be ensured. Okay, which source, which lane, which sync. Okay, so this problem is not going to get detected when your packet is failing. It will get detected at the initialization stage. At the initialization stage, it will be corrected if you have wrongly connected your channels.
Okay. Thank you, Raj. I think this was the. We have more questions, but I'm not sure we have time at this point.
We do have a couple more questions, but in the interest of time, I suggest we take those offline and respond back to persons that have posed those questions. And thanks again for those questions. And thanks, Raj, Ariel.
Yeah.
Let's move to segment 2. I will introduce back Ido Cohen, and we'll continue on. There will be some polling during this segment, so I encourage you to participate in that polling. Thanks very much.
Thank you, Dervla, and thank you, Ariel and Raj, for the detailed introduction on MIPI Alliance mass ecosystem, and specifically on the A-PHY 1.0 and 1.1. As mentioned, my name is Ido Cohen, and I'm the co-chair of the A-PHY working group. And in this session, we will try and provide information on the next steps in A-PHY developments. As written in the title, this session is intended to be an interactive session where we'll present the general direction and consideration of the MIPI A-PHY working group members and hope to get your feedback. So as Dervla mentioned, there will be polls, and we really hope that you can share your feedbacks and comments, and feel free to raise your comments during this session in order to get a more productive meeting. So going forward, so when the working group started this activity, there is on the next generation A-PHY, so the several guidelines were set in order to have a focus and productive discussions. So the working group is looking to maintain development cadence that generated A-PHY 1.0 as the first automotive asymmetric long-reach standard, and had a follow-up, a very quick follow-up of 1.1 as a quick response for the market feedback on the A-PHY 1.0 during the development. So the first goal is to have a specification update that is focused on emerging architecture and use cases. This is coming based on multiple members' feedback. So thus providing the OEM and Tier 1 companies clear path forward for A-PHY based products. The focus is making sure that A-PHY can serve properly zonal architecture and software-defined vehicles, which is becoming more and more common, and of course, better support the modern automotive cockpit environment. Second thing, and as Raj also mentioned it previously, the backward and forward compatibility. So in MIPI Alliance, there is a long tradition of making sure that new files and new products and solutions are backward compatible and allowing easy migration, and A-PHY is no different. The new version will be supporting older version of the PHY and enabling easy migration where and when it is needed. enabling the easy migration and compatibility is an important element and enabler to system design and evolvement of products that have long life cycle. And this is also driving the third goal that we have, to have no changes to the upper layers, to enable easy migration with minimal impact on system level design, that's reducing the need for any or even no changes to system designers when going forward and migrating some of the components based on A-PHY. The last goal that we had is to maintain the high EMC resilience and the low packet error rate as in A-PHY 1.0 and 1.1, which means to have a robust high noise level immunity with ultra low packet error rate of less than 10 by minus 19. And I think that our first poll question today was about the importance of backward compatibility, and I see that at least from the answers that we get, that this is indeed an extremely important topic, as most of the responders answer that it's either very important or extremely important. And so we are happy to see that this is an important item for the industry, and we will make sure that we maintain that and we keep this going forward. So based on these goals, the group had multiple discussions and planning to follow main features of the next generation A-PHY. These are initial starting points for A-PHY development, and the final definitions will be of the specification will be determined based on further discussion inside technical discussions inside the group and multiple feasibility studies that will be done as was done for the first version of A-PHY 1.0 and 1.1. So the first item is the plan to doubling the per lane bandwidth that A-PHY can provide. Of course, both on all type of cables, and reaching 32 gigabit per second for single lane. This is in alignment with the MIPI Alliance long-term goals of generating clear roadmap of higher bandwidth, supporting the rising demand of the automotive ecosystem. And just in parallel, the poll has just been submitted for your feedback on this bandwidth, and we are hoping to get your feedback on that. So please join the poll. The second item is again related to feedbacks coming from the market, from the different members, and increasing the uplink bandwidth. The uplink bandwidth will be raised to more than 1 gigabit per second, and it is again to support the emerging use cases and enhance the uplink capabilities to better fit the zonal architecture and the new cockpit environments. The third item, which is not a specifically PHY related item, but it's more of the overall mass capabilities, and it's updating the adaptation layer that are currently available. So the A-PHY 1.1 added support adaptation layer of Ethernet that's supporting up to 100 megabits per second solutions, and was mainly aimed for display model use cases where interfaces were indicated as needed. Going forward, as the uplink bandwidth is increased, it is possible to support even 1 gigabit per second Ethernet, and the adaptation layer will be updated based on the group analysis of several use cases to meet the requirements of this 1 gigabit Ethernet. The fourth capability is continue enhancement of the security and the embedded security related elements in a similar way that functional safety is embedded within the A-PHY 1.1 and 1.0. This update will enhance the security support and enable new features based on MIPI security work group guidelines. So these are the main new features that we are introducing, and the results of the poll have just been just vanished. But I think that at least the amount that I could see for the 32 gigabit per second indicated that the 32 gigabit per second is a good it's a good goal for the group, especially if you look at the high net data rate. If there is a 90% data rate available for applications, so you get almost 29 gigabits per second of net application data rate for A-PHY based solutions. In the meanwhile, there is another poll running about the ability of having 1 gigabit Ethernet with the MIPI protocols and the usability of having that on a single cable. And I think that is also a very good point that we would like to understand the response and the feedback of the industry. So I will just pause for a second and wait just to we can have to view the poll results, and I hope you can participate in it. Well, while we see that, we'll wait for the poll results. I'll share with you. This is something that been shared with Raj earlier. This is the gear table, the different downlink gears for A-PHY 1.1. And what we expect, and this is again initial position that is still under discussion within the group, is adding new two downlink gears supporting 24 gigabit per second with the net data rate of 21.6 gigabit per second, and a gear 7, which will be 32 gigabit per second per lane with 28.8 gigabit per second max net application data rate. So that's how the downlink table would be looking at. And I see that again, a majority of the responses are that this is very beneficial to edit, and we are happy to see that this is the response, and we will continue with this direction going forward. So as mentioned, this is the planned or current plan for the gear table and the different speeds that is planned for the next generation. What I would like to mention, it should show that the main thing is that as in previous versions, A-PHY will maintain the low bandwidth, modulation bandwidth, in order to maintain lower cost and lower complexity of end-to-end solutions by maintaining the lowest possible modulation bandwidth. So if A-PHY 1.1 and 1.0 were aiming for 2 gigahertz modulation bandwidth, the next generation will be capped with 4 gigahertz in comparison to other technologies. This is maintaining a very low frequency and keeping the system end-to-end. And there were questions earlier about PCBs and cables. So it it has implication both on the PCB design, where you don't need to have high-speed signals running on the PCB, so it simplifies PCB designs, it simplifies cable and harness designs, and it simplifies the overall end-to-end solution going forward. For the uplink gear table, we will add another gear up U3, which will maintain the same modulation scheme as the gear U2, the previous high-speed gear, and increase the modulation bandwidth from 50 megahertz to 400 megahertz. Here we can see the migration between the different gears of the uplink, where in order to maintain simplicity and backward compatibility and ability to evolve the system with minimal impact. So the first migration from gear 1 or U1 to U2, we maintain the same modulation bandwidth, but and the 8-bit, 10-bit capability, and move the system from NRZ to PAM4, thus getting double data rate at the PHY, and even more than double at the net application data rate. When going to the higher speeds, it was important for us to maintain the same modulation scheme, again, to enable easier migration. And by increasing the modulation bandwidth, we can reach the higher data rate and a very good max net application data rate. And that's how we will reach the above 1 gigabit per second max data rate. That will enable both 1 gigabit Ethernet and other control interfaces like SPI, I2C, I3C from MIPI, and many others that could be supported at the same time on this link. So how we are looking at how these new features are actually helping with this new architecture. So zonal architecture is currently considered as a leading approach on the future of automotive advanced system. And it's driven by multiple considerations as harness structure, processing capability, power distribution, and more. At the heart of this approach is the main computing unit that is here described in dark blue in the center of the car. And please forgive my low drawing capabilities, but this is a very schematic diagram just showing the main concepts. And so this is the main computing unit, the dark blue, that is connected to either directly to several sensors like high-speed sensor camera, and two zonal units, zonal ECUs, that are actually connecting to these localized zone units with, they're connected to the main computing unit with high bandwidth connectivity. The zone units are aggregating multiple sensors and actuators that are located in their vicinity, physical vicinity, and may apply or do not, depending on specific use cases, some level of processing of this data before sending it to the main unit. The local ECU is a kind of gateway to multiple devices and should aggregate and propagate multiple types of data protocols and interfaces and to and from the computing unit in order to reduce amount of harnesses and complexity of the cabling harness. So most of the aggregated devices in the zone unit have relatively low bandwidth requirements. And the main devices that we have seen are mainly the cameras that get more and more resolution and require higher bandwidth, and are mostly CSI to MIPI protocol oriented, MIPI protocol and PHYs. And in some cases, you can see also radar and LiDAR sensors that will require such high bandwidth. And the main advantage here for A-PHY is that in these cases, the direction of the high speed is mainly asymmetrical. And the direction is from the end unit to the main computing unit. And thus, A-PHY provides a very good solution for this aggregating the data and being able to provide both the command and control bandwidth of up to 1 gigabit per second and the high-speed downlink data coming from the end devices to the zonal, and with very low processing or very low overhead that is needed to aggregate to multiple devices and direct them to the main CPU unit. So A-PHY brings flexibility to support these multiple interfaces, utilizing different adaptation layers, and have hardware-based aggregation and propagation capabilities that has small memory and software footprint based on our data link layer designs. So this is just another example focusing on some part of the vehicle to reduce the clutter, and you can see all these multiple devices, and the direction of most of the direction is going directly to the main computing unit, and the MIPI A5, which has a native connectivity to the different protocols, specifically the MIPI protocols like CSI2 and DSI2, and has a good comparison with VISA for the DisplayPort, can easily migrate these interfaces into the main CPU unit and enable such easy migration and seamless aggregation of different interfaces with a very high bandwidth for the downlink, and supporting 1 gigabit bidirectional capabilities using the updated uplink. So any bidirectional information up to the 1 gigabit is supported also in this area and also in these areas to the different actuators and sensors, and also being able to go and aggregate, for example, here 2 cameras or camera and the radar, 2 cameras and a radar, everything up to 32 gigabit per second can be aggregated and sent directly to the main computing unit. So, so just to summarize the A-PHY-based zonal architecture. So there is in cases where the main components are going unidirectional to the main CPU unit as cameras and radars, this is the A-PHY provides simplification of the zonal ECU. It has low computing overhead due to the hardware-based solution. It's lower protocol overhead as it maintains the native protocols like MIPI CSI2. And it's designed for ultra low packet error rate at high noise environment. So for the entire lifespan of the vehicle. There was a question earlier about that. So the design is based on assumptions that Of course, there will be degradation of cables. There will be degradation of shielding effectiveness. This was MIPI Alliance held a very long session in independent labs of understanding the impact of these cables and the impact of stress and aging on the shielding effectiveness and the impact on the noise penetration to the receiver. And A-PHY in all generation from 1.0 to the next generation is designed to meet these kind of challenges for the entire lifespan of the vehicle. It's also providing a future-looking design and easy migration path, as it is scalable downlink speed going from 24 gigabit per second to up to 64 gigabit per second when utilizing the dual downlink capabilities of an STQ cable. On a single cable, it could be 32 gigabit per second per lane or 64 gigabit per second for dual lane cables. It is flexible and it has rich protocol support from MIPI protocols to general purpose protocols like SPI, I2C, supporting the command and control interfaces like I3C from MIPI Alliance, and also based on long-term cooperation between MIPI Alliance and VISA. It also supports the EDP and DP capabilities, and of course, others like Ethernet and more. And of course, as a note, the A-PHY working group is happy to receive any feedback on needed adaptation layers or protocol interfaces that can be beneficial, and will be happy to add this kind of adaptation layer to the working plans of the work group. And of course, as mentioned multiple times in this session, it is guaranteed to have interoperability and backward and forward compatibility with the different products based on A-PHY, and of course the different generations. So no problem migrating some of the components to a next generation based on specific use case and still having a very good compatibility with the rest of the system. It is easing the system design and the overall overhead needed in order to support these systems. Going forward, the second use case that was in mind for the work group is to support the modern automotive cockpit, and specifically the cockpit displays that are reaching more and more higher resolutions, getting more and more displays, either it's separate displays or single large displays. But in recent years, and also in the latest shows we've seen and announcements, you can see that many OEMs are driving this cockpit environment to much higher capabilities and resolutions than in the past. Here you can see one example of having multiple displays, like side mirror replacements that are sitting at the sides, a driver instrument display that is replacing the traditional gauge, a center information display. This is, you've seen in many vehicles already today, and extended the driver display for the to the passenger next to the driver. And of course, there are more like lower control display that will add some features, and you can see more and more of these kind of displays. Going forward, there are also capabilities of rear mirror replacement by this display, having connectivity to a back camera that reduces the need to or increases the ability of the driver to see what happens behind the car without relying on a standard mirror, but having a camera there. So, and the resolution are always going up and up. So the A-PHY ecosystem supports multiple connectivity schemes, including and specifically for this kind of usage, the daisy chain. It can support up to 64 gigabit per second non-compressed data in a single port, and up to 192 gigabit per second with applying VESA DSC compression with no additional overhead in a single port. And this is due to the ultra low packet error rate that of 10 by minus 19 is enough to support this kind of compression without any need to add additional protection, as this is almost in the lifespan of a car could be considered as an error-free links. It has a flexible uplink up to 1.6 gigabit per second, and it can enable also, other than just command and control and many other capabilities, it also can support the internal DMS camera, which is the driver monitoring system. So having an uplink of this kind will enable you to, on the same cable, to also support the internal DMS camera. As mentioned, there is a very low packet error rate for the vehicle lifespan, taking into account the aging and stress that is expected. It is previously in the A-PHY 1.0 already, the end-to-end functional safety and the end-to-end advanced layered security that MIPI Security Working Group is providing as a framework for the A-PHY based products. And of course, the multiple protocol support, especially around displays, either it's DSI or DisplayPort. DSI is, of course, MIPI's protocol for displays, DisplayPort, and others, and also the ability to mix and match. There is a capability to go between them and still work properly. So this is a very simple schematic diagram of how the daisy chain is working or is planned to work. So what you can see here, that there are 4 displays connected as in a daisy chain connectivity to one ECU. And the different colors of the packets indicate that from the ECU, for example, we have a link 1 that, for example, supports 64 gigabit per second, and it is connected to a bridge that first takes the the specific data that is coming to the display, and allows the rest of the data to continue. And similarly, this is happening going forward from each bridge to each bridge. And on the reverse direction, the uplink is behaving in a similar way and building this into a single, building these multiple logical links into a single link, into a single physical link going between this. So you can migrate from very high speed on a short or the first leg, and then going down to a specific, for example, this could be a 16 gig in this 16 gig link, and this could be 32 gigabit per link, or could be also 32, and specifically it depends on the needs of the specific displays that are being used there. Of course, this will also be applied when doing compression, and each of the displays, it could have that one display data is compressed, the other one is not compressed. So each logical stream is independent and being streamed over the physical links and being distributed based on the specific goal or specific display that is needed to be supported. So this is one example of more. This is another possible high-end display capability. And you can see that there are three configurations that we have seen here. There is the main ECU, display 1, display 2, and display 3, with link 1, link 2, and link 3. And you can see the different display resolution that were allocated here for the different displays, and the total bandwidth that is needed. So coming from total of 37.6 giga to 96.5 gigabit per second. The bandwidth assumption here is for uncompressed 24-bit per pixel, or the DSC if it's compressed based on CVT2 from the VISA blanking definitions. So what you can see here is that these system can, if applied compression, so the first one that has 37.6, it is reduces by 3 for the DSC and can be supported by APHY as it is today for 1.1. In case there is no compression, so dual link of Gear 6, which Gear 6 supports 48 gigabit per second for the dual lane capabilities. And then the second link after supporting the display 1 will be sufficient Gear 7 single lane, which is a 32 gigabit per second. And then after this, getting to the display 2, the third display could be sufficient to have Gear 5, which is a 16 gigabit per second. In a similar manner, you can reach up to, for this example, 96.5. After applying the DSC, it is compressed to 32.2. And then with the dual link Gear 6, you can support the whole bandwidth, then reduced to Gear 6 and Gear 4 based on the different displays. So that's a very unique and strong capabilities, and this is I think very important to understand that for APHY, due to the very low packet error rate, it is possible to apply the compression without any unnecessary overhead to this net data rate. So we have asked about daisy chain, and I think that most of the answer would be that this is needed in many cases. And I think that now the question about the compression, which is very interesting. So I can see again a very strong support from the people that answered the poll to support the display compression. And I think that this is a very good indication and a very good approach going forward, is in order to support the high needs of the displays in automotive systems. So to summarize, A-PHY is the first asymmetric long-reach optimized video transmission standard for the automotive market. It is a resilient and robust solution for the whole lifespan of the car, designed to meet the unique noise and stress challenges of automotive world. And the next generation of A-PHY will continue to support these And to take that into account, we're going to define the specification. MIPI Alliance is continuously working on A-PHY to meet the evolving needs of the market and to provide complete package to support the ecosystem. And this will come, as we said, also with adaptation layers and other frameworks like security and functional safety. The next generation A-PHY will bring higher speeds, more adaptation layers supporting more interfaces, increased design flexibility, and enhanced security. So with that, I think we have time for Q&A, and I hope it's the direction that we are going through is clear, and any questions are welcomed.
Thanks, Ido. We are a little tight on time. Perhaps we could take one question, maybe two if they're short, as we'll do a brief wrap up and hope to keep on time. Thanks. Ariel, you're on mute.
Thank you, Davla. And thank you, Ido, for the presentation. I think the question will go quickly. Why connecting sensors via A-PHY to ECU and then again to a central unit and not directly to the central unit?
So that's a good question. As I said, I think this is a more questions for the OEMs and Tier 1s for the architecture. Of course, A-PHY will support both capabilities. A-PHY supports A-PHY 1.1 and 1.0 supports cables up to 15 meters, up to 16 gigabit per second, and A-PHY, the next generation A-PHY will support very similar capabilities. So depending, and this is what we mean when we say that we will give OEMs and Tier 1s flexibility. So if a OEM chooses to go with, let's say, domain architecture and connect everything to a domain controller, or connect some of the cameras or other sensors directly to the main ECU, that's supported. And if they choose to have a zonal ECU from their perspective on their architecture, this is also supported. And that's the goal of the MIPI A5, to support to enable the flexibility and to support a vast range of solutions.
Yeah, thank you, Ido. Do we have one more question? Are we directly competing with Ethernet in zonal architecture?
In my opinion, there is a major difference between Ethernet and A-PHY, and there is no direct competition. The question is, again, going back to the type of use cases and architecture selected by a specific OEM or Tier 1. In case there is a need for symmetric communication, this is clearly Ethernet based, and there is no, if there is a need for 10 gig or 25 gig or whatever symmetric solution, probably Ethernet is the go-to solution. If the type of data that is expected is mainly asymmetric, I think that A-PHY would be a suitable solution. So again, we are not competing with Ethernet. We are just providing OEMs more possible solution for a different kind of questions. And I don't think that, I think that Ethernet and A-PHY are a complementary solutions and can work together. And I think this is something that we'll probably see by different OEMs, because there is both use cases that will be served better with Ethernet, and other use cases will be served better with A-PHY.
Yeah, thank you, Ido. I think we had our two questions. The other question has been answered in the chat. Maybe I will hand over to Peter.
Thanks, Ariel. And I'd like to thank the speakers, Ido, Ariel, and Raj. I'd also like to thank the attendees for participation in today's forum. There's certainly a wide range of the ecosystem represented today in the audience, including non-members of MIPI. While we have a number of opportunities during the year, similar to today's forum, to learn about APHY and other MIPI specifications, the best way to engage and evaluate and contribute is to be a member and to participate in the various working groups. So if you have an interest, please feel free to reach out to us. In addition to the development on next generation of MIPI A-PHY, which we talked about today, work is continuing in the areas of security, functional safety, and test, all in support of A-PHY development and adoption. This forum has been recorded and will be made publicly available, as we do for other similar types of webinars, if you'd like to pass it along to your colleagues or others. We find it best and are more than willing to entertain questions from both members and non-members regarding APHY or other MIPI specifications. We also find it best to get and give the information directly from the source, or at least to obtain MIPI's response or position on a particular topic. I live and breathe this every day, and unfortunately see that there's a bit of sometimes misinformation that gets promulgated in the marketplace. And it's natural, it's understandable in an evolving and important ecosystem and competitive ecosystem such as automotive. We welcome the exchange and collaboration, even on what may be considered challenging questions. Please do feel free to reach out to us. We're here, we're open, and we're willing to engage. And I do thank you for your participation and wish you all a successful and safe 2022, and hoping to get to a day when we're all able to meet together again. So appreciate it, and thanks again to the speakers and to the attendees. Have a good rest of your day. Bye-bye.
Thank you very much. Bye.
Thank you.